It's very nice to be here again, giving a talk to this very select group today. And I guess I get to do this from time to time. And I put up on the slide today the University of Limerick, but those of you who know me will know that that's formally. I'm semi-retired now. We're going to talk today about reducing multicollinearity in GLMs when you've got categorical variables in the model. This is joint work with Dave Penn. Dave Penn is in Vancouver. Actually, I got an email from her before I came here today to say that actually she's in Wuhan. So she's originally clearly from China, but she works in British Columbia, and we've been working together since 2005. So say something about the preamble. Better sit down if people are online going to see me. You know that with GLMs, especially in sociology and in psychiatry and in biostats, you sometimes get a lot of categorical variables. And you know how we model those? We model those by using contrasts among the regression coefficients in the model. And there are several schemes available. You can have David Frith's method, you can have a constant sum method, or you can have the reference subclass method. And that's the method I'm going to talk about today, because that's the method that's most common in the literature. You see it in R, you all be familiar with fitting models in R. And there, for each categorical factor, you drop the column associated with the reference subclass, and that has the effect of setting the coefficient according to that subclass equal to 0. But if you do that, if you pick a reference subclass where the numbers are small, that can lead to difficulties. It can lead to unstable models, some of whom might be inestimable due to the multicollinearity, which is the linear possible or near linear dependence between columns, between two columns, or one column and a combination of other columns in the design matrix. So you don't want that. You want to avoid that so that you can carry out the estimation and have reliable estimation. So presumably there are ways of doing this in the literature, and they have been described by other authors. But I'm going to talk about a method which is very simple today, where you can reduce the multicollinearity by a judicious choice of reference subclasses. So if you have M categorical variables in the model, by selecting particular subclasses in each of the variables without any computation, just I'm going to make that one the reference subclass and this one the reference subclass in the second factor, etc., that you're going to effectively reduce the multicollinearity in the model. So the outline is we're going to start with the GLM setting. You're all familiar with that. So this will be wee buns, and it will be a nice lead in, because I'd like you to go away today with a firm idea on how you would do this in practice. It's not going to be rocket science, and you'll go away with something that you can do, I hope. We're going to define a measure of precision, and we're going to define a measure of multicollinearity, and then we're going to worry about how those two things move together briefly. We're going to worry about that. Then we're going to define our approach, and it's a discrete choice approach in several different senses, but that's that's what we'll be involved in. And then we're going to move out of the LM paradigm into other GLMs. I'm going to talk a little about computation and simulation, and analyze a set of real data, show you the analysis and the method in practice. Okay? That's the basic idea. So the linear model setting is very familiar with you. If you look at equation 1, you have a standard linear model. It's a general linear model. And you've got the continuous response, you've got the regression coefficients, you've got the model matrix X, and you've got the epsilon, you have the residuals. And we might, from time to time, assume they're normally distributed with zero mean and constant variance. And if that's the case, then we have the maximum likelihood estimator, familiar form. We have the variance, sigma squared x prime x to the -1, and we have Fisher information. All happy with that. The form of the design matrix now, or the model matrix, suppose we have just one categorical variable with p subclasses, okay? Then we'll have these numbers n1 in the first subclass, n2 in the second subclass, etc. And the design matrix X then encodes these variables. And when it does, x prime x takes the form. Here we have a nice hand that takes this form here. N is the total number of observations, and we have the n's up to nk, and that is well, I'll explain that in a minute. It's a relabeling, but it's fine. So this is a bordered diagonal matrix in this case. So in 5, we have included an intercept term. This is where this form comes from. And we have x1 to xk binary indicator variables. But if I pick n2, then I have relabeled this j running from 1 to k. So we have x0 and we have x1 to xk binaries where the non-reference categories are labeled 1 up to k. You see that? If R is the particular reference category that you pick, R running from 1 to P, okay, then and NR is a number in that category, then the variance covariance matrix is sigma squared x prime x to the -1. It takes that form that you can see on the screen. And the thing I want you to realize about that form is that it varies with R. You see the NR is the particular number in the reference category that you picked. So the numerical value of the variance covariance varies according to your choice of R. Are you familiar with that? Anyone? Is that unusual? Well known? What's your view? You can think briefly on that. Here's an example of that, just to make things firm. There's a categorical variable with p equal to 3, and we have n1, n2, n3 then in the particular categorical variable. And what I've done is I've calculated, let's see if we go this way. Yeah, I've calculated 6. So I have, I'm taking the diagonal from 6, but I've done it for each case of making the assumption that R is equal to 1, R is equal to 2, and R is equal to 3. So these are the algebraic forms of the diagonal. And you can see immediately that these do vary with the reference subclass, a particular reference subclass choice. And if you look carefully at the pattern, you will see how to minimize that. That is how to make this diagonal as small as possible. Okay. Of course, it wouldn't vary with R. The variance covariance matrix wouldn't vary with R if we the optimal solution, that's which n vector minimizes the generalized variance. Well, if you go through that argument, you find that we don't vary when all the n's are the same, and you've got a uniform distribution. But you realize that in observational studies, you don't see that. It's very unlikely that in an observational study that you're going to have equal numbers in all categories, maybe in a designed experiment, but not in an observational study. Okay, so our measure of precision is going to be total variance. And the virtue of this measure is that TR is the trace of the variance-covariance matrix, and TR varies with reference subclass. If we're going to worry about the effect of the subclasses, then we need a measure of variance which varies with the subclasses, so we can judge which subclass will, if we pick it, will result in the smallest variance. So total variance will have that effect. And if we just go back to and look, there are the diagonals, we just add those up, add the elements up to get the trace. And then you can see clearly that they'll be minimized when you pick the largest subclass. And that's what we've said. Pick the subclass with the largest number of observations in it. That will minimize the total variance. Okay. We need now a measure of collinearity. And this is relatively easy because Belsley, way back in 2004, introduced this measure of condition number, where he defined the condition number as K of M, where M was a square matrix. He used X prime X. And we're going to do the same because it's very convenient, because Belsley had these two threshold values indicating medium and serious degrees of multicollinearity. So we thought his measures might be useful. And that's convenient because the condition number of the cross product matrix is the same as the condition number of the variance-covariance matrix, up to a constant. So that's very nice. So those are our two measures, but let's look a little bit at the multicollinearity measure. All right, we have P equal to 3 in this example. There are frequencies, and N is 60, and we are going to have three categories. We're going to have three possible variance-covariance matrices. But these are the cross product matrices in which those covariance matrices would be based. So you can see the three cross product matrices which result with R equal to 3, R equal to 2, R equal to 1. And there are our condition numbers. And you notice that the smallest condition is associated with R equal to 1, and R equal to 1 has the largest number of observations in that category. Okay, so that's interesting. And we notice too that the VIFs, variance inflation factors, these are standard measures used in the literature all over the world to measure multicollinearity. So large VIFs, as they're referred to, are bad, but the VIFs are constant here. It doesn't matter what the values, they're constant. So they don't measure the intrinsic variation associated with the variation in changing subclass, reference subclass. Okay, that's something to note too. So overall, now that we have our two measures, our objective is to minimize these. Now we have precision and we have multicollinearity. These ideas are related, of course, and we are going to be interested in the relationship. But I'm only going to deal to, oops, it isn't. I'm only going to deal today with TR min. This is the discrete choice minima, and this guy here, KR min. If there's a bit of time later, I may mention a global choice minima. So we would like to minimize this chap, and we would like to minimize this chap here. So what about the relationship? Recall that for one categorical variable, we found that picking the subclass was the largest number minimized the total variance. So in the discrete case, which in the discrete choice case, the case we're dealing with, every choice of reference subclass generates a pair. If you pick a subclass, you can calculate the total variance. If you pick a subclass, you can calculate a pair, TR and KR. And with sufficient pairs, you could have a graph, okay? Now, the following ideas in truth. In statistics, it's ideas that count. That's the key idea, having good ideas. So these ideas in truth now, what if these measures are weighted in such a way that minimizing TR, and we know how to do that, also minimizes KR? Okay, maybe in going along this track today, that may seem obvious, but when we came to this at first with the wide choice of different approaches, it wasn't at all obvious to us that this might be a route to go down. But anyways, it was an idea that we came to. And if true, could this idea be applied to models not with one categorical variable, but with m categorical variables? So this was a conjecture, in a sense. If could that be true? And even if it didn't minimize, was it good? Would it be good? Would it be a good estimate of the minima, or would it be dreadful? Well, we didn't know. It's very difficult to find the analytical relationship for high-dimensional models between TR and KR. We have not been able to do it for models much above 2 or 3 subclasses analytically. But here's an example of the type of relationship you find when you can do it. Okay? You find that you have KR here and TR here, and as TR goes down, KR goes down. So we thought it would be a good idea, at least based on the fragmentary evidence that we have here, to explore further in this area. So here was the logic of our approach. We'd like to minimize TR and KR preferably, or KR on its own. We'd like to have some form of minimization. And you know we have the observations to hand. We're still in the linear model framework. And so we can have the cross product matrix, and we can have the variance-covariance matrix for any situation. Now, for one categorical variant, we know that TR is minimized when the reference subclass is picked as that subclass with the maximum number of observations. And we have seen in this case that KR goes down when TR goes down. So using just those two pieces of information, we picked the cross product matrix at the highest, using the subclass with the most observations. We compute V, the variance-covariance matrix at that point, and we compute, of course, the total variance similarly. And then we can compute, lastly, we compute the condition number. For m categorical variables, we're going to do exactly the same thing. Okay, for each of these categorical variables, we're going to say the reference subclass is that subclass for that variable, which is the maximum number of observations. Now we're going to do it for the first variable, the second variable, right up to the nth variable, and we're going to call that a vector of maximum subclasses, okay? And then we're going to go through the procedure that we just went through for one. So we just repeat that piece of logic. So this is achieved just by inspection. You inspect the vectors and you say, okay, that's the maximum, that's the maximum, that's the maximum. But if we think about this not from a statistical point of view necessarily, but from a mathematical point of view, we can search the whole reference subclass space. So we can, if we think about doing that, then we have a choice. If, let's say we have 2, m is 2, and we have the first variable, categorical variable, has 3 subclasses, and let's say the next one has 3 subclasses. So there are 9 possible selections for there's pick the first one and the first variable, and sort of then you have 3 for the second variable, and similarly. So you have 9 possibilities. So for any model, we could, any linear model, we could search the, any model more generally, but in this case, we could search and find the minimum just by a numerical direct search calculation. And then we can ask, how good are the 2 statistics that we computed by inspection, which involve no computation? Are they anywhere near the discrete choice minima? Do you see that? So we can think of the values of T n max and K n max as estimating the discrete choice minima, T min and K min. And so we think these pair estimate the minima, and we denote this situation and this idea and this framework by putting hats on these guys here, and call them our estimators. They're estimators, and they're obtained just by inspection. So that was one step. Are you happy with this? It's a very simple idea. Do you agree? It's a relatively simple idea. Then the extension to GLMs. Now, this is very heavy, mainly notationally, but not in ideas, but it's heavy notationally. So I'm skipping the details that are in the paper. But what it boils down to is, instead of using the maximum, using the subclass with the maximum numbers in that subclass in our framework, don't do that. Instead, use the maximum weight, and it's the product weight. And so it's certainly based on the observation. There's the observations, but it's the observations times this weight. This var phi is the structural weight from the GLM. Now, this will work. Oh, no, back. That didn't work. That's shocking. I'll show you at the end. It's in the last slide, and it's at the bottom, the rightmost bottom corner of the table. But they're taken from the standard weights in structural weights in GLMs. So that's available. That functional form is available, and we just evaluate it, interestingly, at the maximum likelihood estimate of the intercept in the model. Okay, so that does require some calculation, but and there's a workaround that. So just as we chose the reference subclasses using n, we're now going to do it using w, and now we're going to have a vector of these if we have m categorical variables, and so we use these 2 statistics which we can compute as our estimator. And let's see how they perform in simulation. Okay, that's true. Now you may think, how is he going to simulate this? This is really an infinite simulation space if you think about it. So I can't do it all, but I can only begin to explore let's say the foothills of the space. And I explore the useful foothills of this space. So I can have M, that's the number of categorical factors, up to a maximum of 8 in this simulation. I can have subclasses per factor going up to 9. I have explored the 2 series up to 8, the 3 series up to 8. Various selected higher dimensional models, M greater than 2. And you have the model structure and you have the sample sizes. And in the simulation, the sample size is 200, 500, 1,000. Clearly, if it's a high dimensional model, sample sizes of 200, even 500 would be very small, really. All the regression coefficients lie in this range. And the replication rate for the simulation tables is 10,000 simulations, not 1,000, 10,000 simulations. And the GLMs studied the linear model, exponential, inverse Gaussian, logistic model, Poisson, and geometric. Okay. So that's the first thing in terms of results. Can you see those clearly? Good. Right. So what's in the table? Well, firstly, structure of the table. Sample size, 200, 500, 1,000. Across the top, the GLMs studied. Linear model, logistic, Poisson, exponential, inverse Gaussian, geometric. Here, the particular structure of the table study. In this slide, they're all pretty low dimensional models, 2 by 2, 2 by 3, up to 2 by 3 by 4. Okay, so what's in the table? Right, this is what's in the table. These 95, 98, 96.3, what are they? They're percentages, so they are the probability that our estimator formulated, computed by inspection, attains the minimum. See that? Okay. You see it improves with increasing sample size too. But even for a 3-dimensional table, we're really quite good. Okay. So here are other structures, same thing, but other structures. This is our multi-collinearity method. So that's it there. And this is the most complicated model that we looked at, a 4 by 5 by 4 by 3 by 3. And we're still up here, right? So this, for example, this one here has 1,000 observations. This is a logistic model, and we've got a 96.8% chance of attaining the minimum condition number using our simple estimation method. What do you think of that? That's equals. It's not confidence, it's not coverage, it's equals. It attains the minimum because this is discrete choice problem. Here's for the total variance. You see you get similar results. All pretty good. Again, this is the values for low-dimensional tables, and here's the values for the higher dimensional tables. It's a little bit less than it was, but we're interested mainly in the multicollinearity measure because that's the object of the thing, but still good. It's still good. You know, this is more complicated. So you don't expect 200 observations to do very well when the model is bigger. In such a model, there are 720 cells, possible, possible, 720 possible reference subclass, these reference subclass models to be evaluated there. So you don't expect with only 200 observations that you're necessarily going to get. If you thought of this as a contingency table, then you wouldn't expect necessarily a great result. Okay, so how does it work in practice? That's the next thing. I have simulation into the lung cancer treatment study. So there were 855 incident cases of lung cancer in Belfast. Some 414 were treated, that's 48.4%. There'll be some gasps at that, but this study was conducted between 1991 and 1992, and that's just the way it was then, because the cases of lung cancer were seen late, and it wasn't that the doctors didn't treat them, it was that they didn't treat them, it was that they were untreatable. And so we're now having a logistic model for the probability of treatment. Okay, who got treated, who didn't get treated? What factors influence that? So could we improve it? But once we understand what factors are predictive of it, but maybe we could influence something. There were 5 predictors identified: whose status, age group, cell type, metastasis, albumin level. And here are the number of subclasses per predictor: 4 by 5 by 4 by 3 by 3, 720 cells. Thus, a direct search of 720 models is required to find K-min and T-min. Okay, but see our estimators over. Right, here we go. We're going to use the natural reference subclasses first in the logistic model. We've got to fit a logistic model where the researchers picked the subclasses, the reference subclasses for each categorical factor that they thought was most appropriate to them for their interpretation of the data. Okay? So let's look at whose performance status. The things in italics, I hope you can see that normal is italicized. That's the reference subclass. So there were 78 people who were normal. There were 278 who did light work, and 286 who do no work, and there were 213 who were either bedbound or chairbound. Okay, so that was that. Now we'll just look at one more. Look at age, less than 40, 32. That's the reference subclass, and you can see that well, there were 299, 60, plus 311, aged 50. Okay, so when we do that, our total variance is 2.255, and our measure of a multicollinearity is 20.06, which is moderately collinear according to Belsley's criteria. Now, let's switch the subclasses according to our estimation rule that we should use the maximum numbers. The subclasses as reference subclasses, those subclasses that have maximum numbers. So we switch to no work, that's the most. We switch to 311, age 50 plus, that's the most, and so on, all the way down. Then we find that our total variance is halved. And this is the value we get for the multicollinearity. So we have reduced we've more than halved the multicollinearity measure. Okay. So we're doing very well on time here. So we are the lung cancer study overall results. By direct search of all possible reference subclasses, we get the multicollinearity measure 7.98. The natural subclass choice is 20.06. The maximal subclass numbers are preferred method that we are recommending. Okay, it attains the minimum 7.98. Okay. Maximal subclass numbers but one. That's K hat max for that is 10.52. What is that? That is that some medical doctors don't like changing. They don't like changing all the subclasses to the maximum. They have one categorical variable that they must have measured in such a way. It doesn't matter how much you argue with them that multicollinearity would be reduced if you did this. They say, no, I must have age categories like this, and I want, for the purposes of interpretation, I must have that in a certain order. But you can see that even when you don't switch all the subclasses, you still make a saving. You still make a saving in the reduction of the multicollinearity. More than that, if you put continuous factors into the model, okay, we haven't got any continuous factors in this particular logistic model, but if you mix categorical and continuous factors in the model, it's still, and you switch according to our rule, you still get a saving in terms of the multicollinearity. You can attain, excuse me, as much as half as just as we've seen here. That's very interesting. I haven't got a table showing that, but we mention it, so we do in the paper. So we also can find the global minimum. So if you think about the global minimum, what's that? The global minimum is that forget about being constrained by what you've observed. In the all of this work so far, we have been constrained by what has been observed. And you can think then, if we have one categorical variable, then I could search the entire space to get the covariance, to get the cross product matrices by calculating all possible compositions. So I have 60 observations, 3 categories. How does that split down into compositions? I need positive compositions, okay? I don't want any zeros appearing, because if a zero appeared in a category, it wouldn't be in the model. Okay, then I would have all the compositions. They're symmetric, so I only need half, but each composition would generate an x prime x, and we have 3 categories. So each composition in that case would generate 3 models. So the total number of compositions over 2 by 3 in the case that of the example with categorical variable subclasses, and we have search on that. So we don't do that because it's too big. What we do is we have a Monte Carlo algorithm that searches that space, and we do that for these data. The absolute minimum is 4.64, but we can't observe that. We can't make use of that because there's no data have been observed. That's just a theoretical quantity that can be calculated from a table with that structure. Okay. For our lung cancer data, I've computed the condition number, 720 of them, and there's a subclass index along the bottom, and this is the condition number lying between, I suppose, 1 and 22 or thereabouts. In the data, the researchers picked a pattern of subclass indices, subclass reference subclasses, which are indexed along here, that yielded a value of 20.06. So they picked some pattern up here. So they picked a very bad pattern in terms of the multicollinearity of the model. Almost any other pattern, they could have done better. And if you look here, this value is 8. And if you look there, that's 7.98. So if you had seen these data before you set about choosing your subclasses, they may have given you pause to think. And if you were worried about multicollinearity, you could have made some adjustments that gave you a more reasonable value without affecting the estimation of the interpretation of the model in the limit, but ensuring better estimation. There is the. Do you remember the relationship between TR, KR, and TR graph that I showed you earlier? There is the same thing for these data. The graph goes basically something like that. And you could see as TBR goes down, in general, the condition number goes down in these data. So in conclusion, and I think I've got this quite well in terms of time, the method, which is novel, reduces multicollinearity in GLMs. It works well in practice, simple to implement, cheap to compute. They have good properties, these simple estimators, and they have a high probability of equaling the true value. How many estimators have such a good property and very low bias? The other I should have mentioned but didn't. The other figures here are the percentage, these in brackets, are the percentage bias. It's very, very small bias. Okay. Yeah, the low bias. Now, what is interesting is that very often when we are looking at other GLMs, not linear models, for example, the logistic we use, this chap here may be near 1. So it is often the case that WR and NR are the same. And so very often there is no real need to use Wmax. Nmax is fine. And so this chap here is almost as good, very often the same as the other guy, as the more general guy. So I say here in the conclusions, it follows that the use of these two is a good general strategy, one which extends beyond the GLMs that we see here. That's it. Acknowledgements, Science Foundation, Ireland. Okay, that was a long time ago. Here are some references. These references are old because there hasn't been a lot of work in this area. I guess people thought or have thought that multicollinearity was a solved problem or wasn't worth reinvestigating. I don't know. There are some papers that appear on ResearchGate and some questions that appear on ResearchGate about people who are unsure. But the advice in the literature is not clear. It was part of the reason that we undertook this investigation. Well, I first came across this in 1974. We published something in 2014. That was Dave and Pang and I. That was very good. And then 10 years later, we came up with this. Okay. I'll not go into that. Well, that's it. I think that's enough. Yeah. Clear?
So,
And
is that the paper that you've been given up about? The journals?
Oh, yes. I could say a little bit about that. Yeah. There's some people think that in the academic system that the refereeing system contains the seeds of its own destruction, because the quality of statistical refereeing seems to be going down over time. This particular paper, for example, had a very rough ride and has been rejected by many I suppose famous journals. The RSSB said that it had no value. It was of no interest. Okay, that various things to that effect. That was one thing. Well, biometric, we aimed at that miscellanea. They thought it was too modest to be published in Biometrica. Okay, that was fine. SMMR. I know that that's generally regarded as a good journal, and many people have had good papers published there. But in their case, they sent it to two referees who, the first referee seemed very learned and was, I guess, very supercilious, and said that it was ridiculous to put this forward because the structure of the algebra was such that it didn't warrant it. And the other referee that in SMMR had received a cardboard version of the paper, either through the submission system or through the way it was sent to him. I have no idea. He had made some ridiculous comments. But the principal guy, the first referee said about the algebra, and of course we were able to write back and say it's absolute nonsense. If you look more carefully, you would see that the statement that you made was wrong. And we wrote to the editor pointing out that her view of the paper had been coloured by the first referee who had made a mistake. Made absolutely no difference, and so on, a litany of rejections. But it wasn't until we sent it to a group of people who understood about multi-dimensional contingency tables that they began to take an interest in in the work. And so we felt in the end that it was a long slog, but it was maybe worthwhile persevering. Anyway, it gave me some pleasure to get it published, because it means that every paper I've written has been published. So I would, the journals have this idea that, and the editors have this idea that they're there to organize the paper and put it into their journal, whereas I have the idea that I envisage a paper and I see its structure and its aesthetics to get it into the journal the way I want it in the journal. And there's, of course, some happy compromise can be reached on occasion. But the other idea is that it's as if the referees are up here and the people who are contributing the paper are down here, where often it is the case that the contributor knows the subject area and the referees should not have agreed to referee the paper because they don't know enough to referee the paper. Plato said, the wise man speaks when he has something to say, and the fool when he has to say something. So be careful of the reviewers.